Welcome back to module 2 of the course time dependent quantum chemistry. In this module we have gone over we have tried to find out classical mechanical flavor in quantum dynamics. We have gone over Arrhenius-Phase theorem and hydrodynamic formulation of TDSE. Next we will go over Bohmian mechanics. This is the third topic which we will cover in this module. In the Bohmian formulation, what we will do, we will rewrite the TDSE as two equations. So, we had TDSE, we started with TDSE. These are all different formulation of TDSE. We started with TDSE, time dependence Schrodinger equation. Here x is a function of psi is a function of x and t, and we will rewrite this equation into two equations. One for the probability density and another one for the phase function. And this phase function, we will see that in Bohmian mechanics, this phase function will give me the velocity or the local velocity. It is called local velocity or Bohmian velocity. What does it mean? I will discuss that one. So, from phase function I will get the local velocity. We have understood that variable separation method which we have previously used under the assumption that Hamiltonian of the system, it does not depend on time. Under this assumption we have done variable separation method, and from variable separation method we have been able to get the solution to the TDSE, and we have got one solution which is called stationary state solution. We have got by this, where we have this time dependent phase factor introduced, and E represents the energy of the particle. This is just review of what we have already understood. This psi x is position dependent stationary state of the particle. As every experimental observables are associated with the probability density of the particle, probability density of the particle is represented by this rho x t, which is nothing but psi x t absolute square. So, every experimental observables is actually related to this psi, to this rho, not to this psi. The probability density of the particle expressed by this equation, which is coming from this psi, does not depend on time, and that is why it is called stationary state. So, stationary state has time dependency for the wave function, but not for the density, and because density is something which we observe experimentally we do not see any time dependence. Time dependence, in order to observe time dependence, we have understood that superposition state is very important, and it is expressed by this linear combination of different states, stationary states. with its expansion coefficient. Now, this is we have already understood, and that makes rho x t to be dependent on time. It can be function of time for only superposition state. So, what does it mean? It means that at t equals t1 time, I have some density, this is rho versus x. Again at t equals t2 time, I have some other density. So, then density is changing as a function of time, x and t. As a function of time, density is changing, it means that I have the dynamics in the quantum system. Now, when we said that this linear combination can be used, this equation itself, even if I take two stationary states, this equation can be very complicated. So, instead of such a complicated wave function which will represent the dynamics of quantum system, one can propose that, okay, let us assume that the trial wave function looks like this. Trial wave function has amplitude as well as time dependent phase. So, this A x is the amplitude and S x t is the phase function. And we will assume that both of these functions are real. This is the assumption we are making for the time dependent wave function, because this time dependent wave function, remember, we will, if I take the rho of this time dependent wave function, I still get time dependency in the density, and time dependency in the density, it means that this wave function is suitable to represent quantum dynamics. As opposed to this stationary state wave function, although note the similarity between this wave function and this wave function. It has a time dependent phase factor, it has some kind of amplitude which is time independent, but here only difference is that I have time dependent amplitude. So, both are changing as a function of time, and that kind of wave function can be very useful to represent my quantum dynamics. So, instead of taking this superposition state wave function, complicated linear combination of wave function, one can propose that one can use this as a trial wave function and then plug that in to TDSE and get the solution for that, for the particular system. So, because this A and S, they are unknown function, we have to find out what kind of form we have in this function. So, we have to plug that in, this wave function is to be plugged into the TDSE, time dependent Schrodinger equation, and that is exactly what we are going to do. So, Schrodinger equation TDSE is I h cut time derivative, and then I have the space derivative, this psi. So, what we will do right now, we will take the time and space derivative separately. So, first we will take the time derivative. This time derivative is going to be e to the power I by h cut s x t plus a I by h cut time derivative of the phase function multiplied by this exponential part. So, this is time derivative, and then we will go for the space derivative. If we take the space derivative, it is going to be the first e to the power I by h cut s x t plus a I by h cut space derivative. Then I have to take the second derivative because Hamiltonian operator has second derivative in it. So, I have to take the second derivative. E to the power I h cut plus I by h cut e to the power I by h cut plus I by h cut e to the power I by h cut. This is first derivative with respect to this term, then this is the first derivative with respect to that term, and then I have to take the first derivative, second derivative. This is going to be second derivative of this term, and then finally, so this one is done, and so then this one is remaining, a I by h cut, then again a by I by h cut e to the power I by h cut s. This is just a tedious mathematical derivation, but one can easily do that. So, now we will reduce it further. We have now second derivative with respect to x e to the power I h cut s plus this term we have twice. We have another term missing here. We had plus, this term would be coming twice. So, that is going to be dA dx I by h cut dx e to the power I by h cut xt. So, these two terms will be twice. So, we write down e to the power I by h cut plus plus I have double derivative so this is just A, this is just A, so I have A I by h cut to the power I by h cut x t plus, now this part going to be negative because we are going to multiply I by I here. So, this is going to be negative A by h cut square whole square e to the power I by h cut s x t. So, this is what we have reduced. This is just tedious, one can do it very quickly, and all we have to do is that now we have second derivative with respect to space and time derivative we have. So, we will be able to plug that in TDSE. If we do that, then what I get is I h cut, then time derivative, that is going to be dt e to the power I by h cut s x t plus a I by h cut e to the power I by h cut s x t. This is equals to minus h cut square by 2m. Then the second derivative part. Second derivative part is the entire term, that is going to be e to the power I h cut s plus 2 e to the power I s plus a I by h cut second derivative of the space phase function e to the power I by h cut s minus a by h cut square whole square e to the power I by h cut s. So, this is the entire term for the second derivative plus the kinetic energy part, and then we had potential energy part. So, this is combination of kinetic energy and potential energy. So, that potential energy part I write down V a e to the power I by h cut s. This is the final form of the TDSE. So, all we need to do now in this equation, on the left hand side I have some real part and on the right hand side I have some real part. So, that needs to be equal. On the other hand, on the left hand side I have some imaginary part, on the right hand side we have imaginary part, we will make them equal. So, we will just equate separately real and imaginary part. We will look at the imaginary part first. So, this was the equation which we have got in the previous slide, and if we look at the imaginary part is going to be following. This part is going to multiply it by I h cut. So, this part is going to be real part and imaginary part is going to be this part. So, this is going to be imaginary, then this is imaginary, this one is imaginary, yeah, these are the imaginary parts, and one can also notice that I can remove this exponential part from each term. They can actually be eliminated. So, I will just go ahead and equate the imaginary parts where I have h cut time derivative equals minus h cut square by 2m. So, this 2 will be gone. So, I do not need 2m by m, then dx. So, we have this h cut by m dx, then the derivative of the s function, and then I have this imaginary part, this one. So, these three are imaginary part. So, I have this minus h cut divided by 2m a second derivative with respect to x, or I can rewrite this one as plus 1 by m plus a by 2m second order derivative. This becomes 0. So, the probability density, this is the equation after equating the imaginary part. The probability density for a particle is represented by for this particle probability density will be represented by, because psi xt has a form of a xt e to the power I by h cut s xt. So, density will be represented by nothing by a square, and I said that a is real. That was the assumption we have made. So, because it is real, it is nothing but the a square, and if it is a square, I will be able to find out time derivative of the probability density, that is going to be 2a dA dt, and similarly space derivative is going to be 2a dA dx. So, now what we will do here, we will just multiply this equation by 2a. If we multiply this equation by 2a, then what I get, 2a plus 2a by m plus a square by m second order derivative equals 0. Now, I can insert this one and this one here. If we do that, then I can see that 2a time derivative is nothing but its this function plus 2a space derivative. Here I have 2a and space derivative. So, this is nothing but 1 by m plus a square is nothing but rho by m So, I have been able to reduce this one, and I can further reduce it. This is nothing but time derivative plus this can be written as rho by m we can write down this one. So, this two term can be written as derivative of a product, and as a result one can finally write down dt equals minus of rho by m space derivative. Now, we will recall the hydrodynamic formulation of TDSE. Previously, we have done that hydrodynamic formulation where we have presented rho density, change of density as a function of probability current. So, we have shown that change of probability density is nothing but negative of the gradient of the current at that point, and particular definition of J has been given already. So, we are not giving it right now. So, one can say that this is nothing but rho by m dx, or J has now new definition in Bohmian mechanics. J is nothing but this part. So, we can recall that rho is unitless, it is a probability density. This is unitless quantity, and J represents some kind of velocity in one dimension. So, if this is velocity, then one can say that this entire term which is given here is representing the velocity of the particle. This is called local velocity or Bohmian velocity. So, what we have got is some kind of velocity information we have got for the particle which is moving, and what does it mean by this velocity? We will go over it in the next session.